On this question, they're asking us to convert the complex number in rectangular form to polar form, like r cos theta I sine theta. Enter exact values for r and theta. Okay, so give your answer in polar form, boom, boom, boom. How do we do it? How do we go complex number, rectangular form to polar form? How do we do it? Well, change the rectangular form of a complex number to polar form. This is the notes. This is the notes, the number 9 on the notes. These are the same instructions number 4. But first off, you plot the point, calculate r, and then do the theta inverse tangent thing. Okay, so here we go. So step 1, r equals, oops, that's a funny square root, huh? Square root of x squared plus y squared. Square root, what is x? This is x, and this is y, right? So, I need a little bit bigger square root here. So I'm going to go 5 root 3 over 2 squared plus 5 halves squared. Okay, now here's the key. Normally we just hit the buttons on our calculator and we could just get a decimal. But on this question, they're asking us to get exact values. That's the trick, exact values. I mean, we can't do decimals. So what are we going to do? Then we got to work it out by hand carefully. So that always means being really careful with the whole thing. So I've got to take this 2 power and I got to square the 5, remove the root, and square the 2. So that'll become 25 times plane 3 over 4 plus, and then square the 5, square the 2, 25 over 4. Did you track with it? See the root was removed. It cancels the root. Doesn't square the 3, just removes the root. Remember all that? And so we get square root, what's that going to be? 75 over 4, 3 times 25, 3/4 is 75 cents, plus 25 over 4, which is 100 over 4, which is the square root of 25, which is 5. So the r value is 5. So I guess we could have used our calculator and it would all come out to just be 5. That's fine. Okay, so the r is 5. So now step 2, we could do the inverse tangent thing. And so that's where we go. Reference angle is inverse tangent absolute value y over x. So inverse tangent absolute value, well, I'll just make them positive. Y, 5 halves over x, which is 5 root 3 over 2. Okay, so how do we simplify that? Well, you know, fraction over fraction, grab the denominator, flip it up, right? Dividing is inverse multiplying, upside down multiplying, so it becomes tangent inverse of 5 halves times 2 over 5 root 3. See how I flipped it upside down? This came upside down, we're multiplying. All right, and then the 5's cancel, the 2's cancel, and so this is inverse tangent of 1 over the square root of 3. Now, let me help right here. Here's where it can get sticky and confusing for people, I know. There's a couple of things, there's an easy way to do this and a hard way. The trick is they want exact values, right? No decimals allowed. So if you just hit tangent inverse on your calculator, you're going to get some kind of crazy decimal thing. And you're going to be like, what's that? I don't even know what that thing is. I think it'll be like, some kind of crazy decimal. So instead, instead do this. Change to, let's say, put the calculator in degree mode. And they might say, no, Mr. They want radians. They want radians here. I know. But put the calculator in degree mode because it is easier to see exact values, then change to radians at the end. And do that using the unit circle. That's the game plan. That's the easy way to do this. So hit the so in it's going to be tangent inverse of 1 over root 3 in degree mode, even though we want radians in the end, degree mode on your calculator. I'm going to do that right now on my calculator. Make sure I'm not making up something. I'm going to put my calculator in degree mode, and I'm going to go tangent inverse of 1 divided by square root of 3. I'm getting 30 degrees. Now, if I did that in radians, I would get basically pi over 6, which looks like 0.5, blah, 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 blah. And I probably won't even recognize that it's really pi over 6. If you do, great, but most people don't recognize that. So do this, get this degree. Now, we can easily change that using the unit circle in a minute to a radian, an exact radian answer. We can't give the decimal, right? So that's why we changed to degrees. Now, we're not done. That's only the reference angle. Remember the nodes? That's just the reference angle. But then currently we only have the reference. To find the actual angle, you got to go back to the quadrant and do the formula thing. Okay, now what quadrant is this one in? Oh, we got lucky. This one is a first quadrant. Let me graph it anyway, just to show it. I got lucky on this one. This one is first quadrant because mine is 5 root 3 over 2 up 5 halves. So it's here. It's in the first quadrant. Plus 5 halves I. It's first quadrant. So since it's first quadrant, the actual angle is the same, isn't it? Now, if it was second, third, or fourth quadrant, you know about those different formulas. We'd have to adjust it. 180 minus the reference for second quadrant, plus for the third, 360 minus for the fourth. You know all those formulas. So the actual angle is 30 degrees. Now, last step, change to radians. How do you change to radians? On the unit circle. Just go to the unit circle. You don't need to do any fancy calculation. 30 degrees, 30 degrees, 30 degrees. Let me erase what I did previously. 30 degrees is right here. 30 degrees, pi over 6. It's pi over 6. That easy. That's where we can convert. So this equals pi over 6. So that's the exact radian angle, pi over 6. So we go back, we say, okay, our R is 5. Put that in here. And our angle is pi over 6. So there's exact values, no decimals, exact values in radians. So that's how we do this. Everybody seeing that trick? You got to do the reference angle, but you got to put your calculator in degree mode. So you get a degree, which is more easily recognizable for exact values, and then get the actual angle, ours coincidentally with first quadrant, and then change it back to radians on the unit circle. That's the easy way to get an exact value. And so there we go.